We are Team Garud from the University School of Automation and Robotics at GGS IPO, New Delhi, India. And we are proud to present our Ross Ranger mini project, an advanced autonomous mobile robo, also known as AMR. Before we dive into the technical specifications, we'd like you to meet the minds behind the machine. Our team consists of 5 members, each with their own technical specialty. We have Harshit, Vishal, Parth, Harneev, and Shlok, the group who put in an all out effort in building this project. In this team, Harshit led the mechanical design, Vishal engineered the embedded systems and wireless connectivity, Parth developed the ROS software and SLAM algorithms, Harneev integrated all the hardware and sensors, and Shlok made the mobile app for remote operation. We hope you enjoy our video and learn something new today.
Autonomous mobile robots represent a paradigm shift in intelligent automation. Fundamentally different from traditional guided vehicles, these sophisticated systems navigate dynamically using advanced sensors and artificial intelligence, adapting to their environment in real time. AMRs are transforming industries at an unprecedented scale, revolutionizing warehouse operations, optimizing healthcare logistics, and advancing agricultural monitoring systems. Unlike conventional automation, they think, learn, and make decisions independently. The global AMR market, valued at around $21.5 billion, is experiencing remarkable 23.7% annual growth, reflecting their critical role in Industry 4.0. From manufacturing efficiency to autonomous deliveries, AMRs are not just the future of robotics, they are reshaping how we approach intelligent automation today.
To get started with the particle photon 2, the first step is to register on the particle website. Once registered, you can check whether your device is connected through particle console like we see here. In our case, the device appeared right away, confirming successful connection. For development, I install Visual Studio Code and set up the particle CLI, which allows sending commands directly through the terminal. While working with the Photon 2, it's also important to understand its RGB LED indicators, as they reflect various modes like setup, connection, and error status. There are two main options for programming the Photon, using VS Code or the Particle Web IDE. Although I initially tried VS Code, I encountered a few issues, so I switched to the Web IDE, which offer a simpler and more intuitive interface. One key advantage is that it's already linked to the particle cloud, so there is no need to write an additional code for Wi-Fi or cloud connection. I just wrote the firmware, selected the device, and flashed it directly to the Photon 2.
In our project, we used MIT App Inventor to create a simple mobile app that communicates directly with the Photon 2 via the particle cloud. This allows us to control the robot remotely over the internet using clean, touch-friendly controls. We started by visiting appinventor.mit.edu website, signed in with a Google account, and created a new project. The user interface was designed using drag and drop components, buttons labeled with forward, backward, left, right, and stop. In the block section, we program each button to send an HTTP post request to a particle cloud function hosted on our Photon 2. The format we used was like this. The post body contained the desired command and our access token like this. For each button, a different argument value was used, such as forward, backward, left, right, and stop. These arguments were interrupted by a firmware running on the Photon 2 to control motor movement. To retrieve the device ID, just log into the particle console, select the device, and copy it. For the access token, we used these. Along with this, we also integrated a camera module with the robot. This camera captures live visual data from the robot's environment, which we used as a video feed input in our raw simulation. This allowed us to visually validate the robot's behavior and navigation path in a real time during testing and development. Finally, we tested the app using MIT AI2 Companion to live deploy the interface onto an Android phone. With this, complete setup, we built a cloud-connected AMR that not only receives mobile command but also stream visual input for use in simulation and AI tasks.
One of the core components of our AMR project is Visual SLAM, and for this we have been using Orb SLAM 3, one of the most advanced and versatile SLAM algorithms available today. SLAM, or simultaneous localization and mapping, allows a robot to build a map of an unknown environment while tracking its own position in real time. Unlike traditional SLAM systems that depend heavily on expensive lidars or depth sensors, Orb SLAM 3 is purely vision based. It works with monocular, stereo, or RGB cameras, making it highly cost effective, especially for budget sensitive applications like ours. Now, here's why Orb SLAM 3 is truly special and a perfect match for our use case. First, it supports multi map tracking and loop closing. This means it can seamlessly detect when the rover revisits a previously seen location and adjusts the map accordingly, reducing drift and improving accuracy over time. Secondly, it offers full support for real time localization even in large or dynamic environments. Whether the robo is moving fast or operating in a cluttered space, or SLAM 3 remains stable. Third, and this is a game changer, OpSLAM 3 is the first open source SLAM system to unify visual inertial, and multi map capabilities in one framework. This gives us a lot of flexibility as we scale or modify the project. We are not locked into one type of sensor or dataset. In our simulation, OpSLAM 3 is running on synthetic camera feeds and successfully tracking the robo's motion across rooms, generating sparse 3D maps in real time. This helps us verify that even without a lidar, we can achieve precise mapping using only a camera and smart algorithms. By choosing OpSLAM 3, we are cutting hardware cost without compromising on accuracy, and we're laying the foundation for autonomous operations in complex environments. In future iterations, we can even extend the system to support visual inertial fusion or multi-robo mapping, all within the same framework. So for now, OrbSlam 3 is powering a robo's eyes, giving it the ability to perceive, map, and move confidently even in GPS denied or unknown spaces.
The future of robotics is arriving faster than ever imagined. Picture robots that learn and share knowledge with each other, creating an interconnected network of intelligent machines. Our Ross Ranger Mini will evolve to recognize objects and people, making decisions that seem almost human like. Imagine multiple robots working together like a perfectly coordinated team, sharing maps and coordinating tasks without any human intervention. These robots will process information instantly right where they are, making split second decisions for the better performance. With high speed internet connections, they'll tap into cloud based intelligence, becoming smarter every day. The robotics industry is exploding, growing from $71 billion to $150 billion by 2030. Soon, these intelligent machines will help in rescue operations, monitor our environment, assist in farming, and become a part of smart cities. We're not just building robots, we're creating the foundation for a world where intelligent machines work alongside humans, making life safer, more efficient, and remarkably more connected than ever before.
For the conclusion, our Ross Ranger Mini represents the vision of accessible and intelligent automation. By combining the cutting-edge technologies like the particle photon to intuitive mobile interfaces through MIT App Inventor and robust cross simulation environments, we have created a scalable platform for autonomous operations. This project demonstrates how emerging technologies can be integrated thoughtfully, which can lead to solve real-world challenges in industrial, agricultural, and educational sectors. As we continue to innovate, the Ross Ranger Mini stands as the proof that the future of robotics is not just autonomous, but intelligently connected and remarkably accessible.